Hello, my name is Mohammadreza Haghpanah. I'm a student at the University of Texas at Dallas. Thank you for listening to my talk. Today I'm going to talk about computing the Carathéodory number of a point. My co-author of this work is Professor Sergey Bereg. Let's start with the well-known Carathéodory theorem. It says that any point in the convex hull of a set of point P in Rd is in the convex hull of a subset phi prime of P such that the size of phi prime is at most d plus 1. Look at the following figure. In this figure, there is a set of points in the plane and a point in the convex hull of the set of points. By Carathéodory's theorem, point P is in the convex hull of at most 3 points of the set P. Here is an example of such points. However, there is another subset of set P of size 2 such that the point P is in the convex hull of it. This is related to well-known concept of Carathéodory number of a set. Carathéodory number of a point P with respect to a set P is the size of the smallest subset P prime of P such that the point P is in the convex hull of P prime. Carathéodory's theorem guarantees that for every set of point P in Rd and point P in the convex hull of the set P, the Carathéodory number of the point P with respect to the set P is well defined and is at most d plus 1. This is related to the well-known concept of the Carathéodory number of a set. The Carathéodory number of a set is being studied for more than 90 years in more general setting. Here we define the Carathéodory number of a set using the Carathéodory number of a point. Carathéodory number of a set P is the maximum of Carathéodory number of points in the convex hull of the set P. We will see one of the results related to Carathéodory number of a set in the following slides. In this presentation, we are interested in computing the Carathéodory number of a point. We study the computational problem of finding the Carathéodory number of a point with respect to a finite set. In computing CNP for a set P and a point P in its convex hull, we want to compute the minimum size subset P prime of P such that the point P is in the convex hull of P prime. Bahrani generalized Carathéodory's theorem by using a family of d plus 1 sets which are called color class such that their convex hull intersect. We call the set of d plus 1 points, one from each color class, a colorful choice. The colorful Carathéodory's theorem states that for a point P in the intersection of a family of color classes, there exists a color choice P prime such that the convex hull of P prime contains the point P. One may ask whether the number of colors in the set P prime can be reduced. We call a set of at most d plus 1 element, one from each color class, a rainbow. A rainbow is a subset of color choices for family P. The colorful Carathéodory number of a point P with respect to a family of color classes is the size of the smallest rainbow which contains point P in its convex hull. As an example, in this figure we can see the point P is contained in the intersection of 3 color classes, each with 3 points. So by Carathéodory's theorem, we know that there exists a colorful choice with its convex hull contains P. But as is seen in this figure, a rainbow of 2 points is sufficient to satisfy the statement of colorful Carathéodory's theorem. We are interested in computing colorful Carathéodory number of a point. So we defined computing CCNP similar to computing CNP. Here we summarized all the results. We characterized the Carathéodory number of any non-empty set in Rd. We showed that the decision version of computing CNP is NP-hard if the dimension D is part of the input, and it is KLDT-hard if the dimension D is fixed. We present 2 algorithms for computing CNP in the plane and R-cube. Then we extend our results for computing CNP to computing CCNP. Now we want to discuss our characterization of Carathéodory number for sets. As we already stated, there have been much research on this concept. For example, Fenchel proved that a compactium in Rd either has a Carathéodory number less than d plus 1 or can be separated by a hyperplane in 2 non-empty parts. Fenchel result can be used directly to determine the Carathéodory number of these 2 figures are less than 3. We have proved the following proposition, and due to the simplicity of its proof, we don't discuss it and refer to the paper. This proposition states that the Carathéodory number of any non-empty set P in Rd is one more than the dimension of the Affine-Hall of a set P. Note that the Carathéodory number of a finite set in Rd can be computed using this proposition. Next, we talk about hardness results. Decision version of ComputingCCNP can be formulated as follows. Given a set of points in Rd and a point in the convex hull of set P, and an integer k, we decide if Carathéodory number of the point P with respect to the set P is less than or equal than k. Observe that deciding CNP can be solved in polynomial time if this dimension d is a constant. We show that it is NP hard if d is a part of the input. We reduce the exact cover by 3 sets problem to deciding CNP problem. In exact cover by 3 set, we are given a universal set of m elements where m is a multiple of 3 and a collection of subsets of it, each of them of size 3. And we want to decide if there is a partition of the universal set using a subset of the collection. Exact cover by 3 set is a variant of exact cover problem, and it is known to be NP complete. In the left figure, we demonstrated an instance of exact cover by 3 sets with 6 elements and a collection of 5 sets T1 to T5, each containing 3 elements. For example, T1 contains 1, 2, and 4, and T2 contains 1, 3, and 5. We construct an instance of deciding CNP as follows. We define a matrix with m rows and n columns, which in this example give us a 6 by 5 matrix. And the ij entry of this matrix will be 0 if the point I is not in Tj, and will be m over 3 if point I is contained in Tj. Each column of this matrix represents a point in P in deciding CNP problem. Also, let P be one column matrix of size m with all entries equal to 1. We showed that there exists an exact cover for the universal set if and only if there exists a subset of set P of size k where point P is in the convex hull of it. To see this in our example, it's enough to check that T1 and T5 is a partition for elements in exact cover by 3 sets. And corresponding to that, there is a vector 1 over 2, 0, 0, 0, 1 over 2 as convex coefficient of points capturing point P. Now we want to discuss our algorithm concerning whether Carathéodory number of a point is a certain number or not. Deciding whether Carathéodory number of a point is 1 will be easily done in O of n. So we start by the problem of deciding whether it's equal to 2 or not. We set the assumption that the dimension is a constant. We provide an algorithm to decide whether Carathéodory number of a point is equal to in O of n log n. And also we showed that this is an optimal algorithm in algebraic decision tree model. The idea of the algorithm is to first normalize and project points on the unit sphere. Then it's enough to check if for any projected points, negative of it is in the set of projected points or not. We do this by performing a binary search on lexicographically sorted sequence of projected points. Next, we discuss deciding if Carathéodory number of a point in our cube is equal to 3 or not. We have shown that this problem can be solved and found corresponding set in O of n squared log n. For this purpose, we first use previous algorithm to check if Carathéodory number of a point is less than or equal to 2. If not, we try to check if Carathéodory number of the point is equal to 3 by checking if there exists a triangle consisting of points in the set P which contains the points. Here is the idea of the algorithm. For each point pk, we compute the plane pi k, which is the plane passing through point P, and vector ppk is its normal vector. Then we project other points on the plane pi k and perform a pruning step to remove some of the points. Then we compute all the candidate sets using projected points and check if any of these sets give us a solution. Here we talk about pruning step. We consider angle alpha for a point pi be the smallest angle between vector ppi and ppk. To perform pruning step, for each 2 points which their projection on the plane pi k have the same direction, we keep the one which has the largest alpha angle. In this figure, there are 2 directions d1 and d2. For an example, points p1, p2, and p3 have the same direction. In the pruning step, points P1 and P2 are pruned, and points P3 get survived. Similarly, point P7 gets survived in the other direction. We showed that the remaining points after pruning step is sufficient to construct a triangle contains point P. As seen in this figure, the set PK, P3, P7 contains point P in its convex hull, although points P3 and P7 are the only remain point after the pruning. Finally, we showed that our result for computing CNP can be extended directly to computing CCNP. We showed that the decision version of computing CCNP is NP-hard. Similarly, one can prove that deciding CCNP is KLDT-hard if dimension D is fixed. We showed that the algorithm for Carathéodory number of a point can be modified to colorful Carathéodory number of a point with the same time complexity. Thank you for your listening.